Have you ever imagined holding the entire sum of human knowledge inside a container the size of a pong ball? I'm not talking about a futuristic hard drive or a memory stick. I mean physically storing every movie ever filmed, every song ever recorded, and the entire internet as it exists today inside a few drops of liquid. It sounds like science fiction, but as we rapidly run out of the silicon needed to build computers, this biological miracle is becoming our only hope to save the world's data from extinction. Let's dive in. We are standing at the edge of a precipice. It is a crisis that almost no one is talking about, yet it threatens the very foundation of our modern world. We are running out of space. Not physical space for housing or farming, but space for our memory, the digital memory of the human race. By the year 2025, humanity is projected to generate 181 zettabytes of data annually. Now, zettabyte is one of those words that sounds big, but is hard to truly wrap your head around. So let's break it down. 1 zettabyte is a trillion gigabits. So 181 zettabytes is roughly the equivalent of creating 1.5 trillion gigabytes of new data every single day. This isn't just cat videos and Instagram posts. We are talking about the Internet of Things. Sensors, self-driving cars, smart cities, plus the massive wave of data being generated by artificial intelligence. And here is the terrifying reality: we physically cannot build enough hard drives to store it all. If we tried to store the amount of data predicted for the year 2040 using our current best technology, enterprise-grade flash memory, we would need approximately 100 trillion kilograms of silicon wafers. To put that into perspective, that demand exceeds the entire world's projected supply of silicon wafers by 6 orders of magnitude. We are hitting a geological limit. We literally cannot mine and refine enough silicon to remember our own future. And even if we could find the materials, we couldn't afford the electricity. Right now, data centers consume about 1.5% of the world's total electricity. That might sound small, but with the AI boom, that number is set to double by 2030. In the United States alone, data centers are on track to consume 9% of the entire country's power generation. We are building energy-hungry warehouses just to keep our digital history alive, spinning hard drives and cooling servers 24/7. The current infrastructure is unsustainable. We need a new medium. Ideally, we need something that is incredibly dense, uses zero energy to store data once it's written, and lasts for thousands of years without degrading. It turns out the perfect solution has been right in front of us, or rather inside of us, for billions of years. It's deoxyribonucleic acid, DNA. This is the concept of bio-digital convergence. It is the idea that the molecule that encodes life is actually the ultimate hard drive, and the numbers back this up. DNA is fundamentally a digital storage medium, but whereas our computers use a binary code, zeros and ones, biology uses a quaternary code. It has 4 chemical bases: adenine, cytosine, guanine, and thymine, A, C, G, and T. Because DNA exists in 3-dimensional space, rather than on a flat 2D silicon chip, its information density is mind-boggling. The theoretical limit of DNA storage is 455 exabytes per gram. In practice, researchers have already demonstrated a density of 215 petabytes per gram. Let me give you a visual for that. If you took every movie ever made, every song ever recorded, every financial transaction, and the entire internet as it exists today, you could fit all of that data into a container the size of a ping-pong ball. A single cubic millimeter of DNA can hold an exabyte of data. That is approximately 500 million times denser than the best magnetic tape archives we have today. But density is only half the story. The other half is durability. If you have ever found an old hard drive in a drawer and tried to plug it in, you know the panic of wondering if it still works. Hard drives have a lifespan of 3 to 5 years. Solid-state drives might give you 10. Even magnetic tape, which is the gold standard for banking and government archives, only lasts about 30 years before it starts to chemically rot. This forces IT departments to migrate data, copying exabytes of files from old tapes to new tapes every 7 years. It is expensive, it is risky, and it is a massive waste of time. DNA, on the other hand, plays by different rules. We have successfully sequenced DNA from mammoth molars that are over 1 million years old. We have found environmental DNA in Greenland that dates back 2.4 million years. And this wasn't DNA stored in a climate-controlled data center. This was DNA left out in nature. When DNA is dried out and sealed in glass, it doesn't degrade. It has a half-life of over 500 years in non-ideal conditions. This means we could write the sum of human knowledge into a test tube today, bury it in a vault, and a civilization thousands of years from now could read it perfectly with zero data loss. It is the ultimate, write once, read never, archive. So how do we actually do it? How do we turn a digital JPEG or a text file into a biological molecule? It starts with the codec, the encoding pipeline. We can't just simply swap a binary 0 for an A and a 1 for a C. Biology is messy. DNA strands have biochemical constraints. For instance, if you write a sequence that has too many of the same letter in a row, like AI, the reading machines get confused and slip, causing errors. Also, the molecule needs to be stable, which requires a specific balance of GC versus 8 bonds. To solve this, computer scientists use advanced mathematics like fountain codes. Imagine taking a file and breaking it into thousands of tiny droplets. Then you add extra mathematical droplets, redundancy. This means that later when you read the data back, you only need to catch about 90% of the droplets to reconstruct the entire file perfectly. This allows us to store data with incredible accuracy, even if some of the DNA strands break or get lost. Once the data is encoded into a string of letters, we have to physically build the molecule. This is the write phase, and it is currently the biggest bottleneck. Traditionally, we used a method called phosphoramidic chemistry. It's a chemical process that builds DNA base by base, but it produces toxic waste, uses harsh solvents, and it is incredibly slow. It's also wildly expensive. Writing just 1 megabyte of data this way can cost thousands of dollars. But a revolution is happening here too. We are moving toward enzymatic DNA synthesis. Instead of forcing chemicals together, companies like DNAscript and ANSA Biotechnologies are using enzymes, specifically an enzyme called TDT, to grow DNA strands in a water-based solution. It's the same way your body replicates DNA, just hijacked for data. It is faster, it is green, and it is much cheaper. There are even more radical approaches. A company called Catalog Technologies is building a machine that looks less like a biological lab and more like a printing press. Instead of building DNA letter by letter, which is slow, they have a library of pre-made DNA fragments, like prefabricated words. Their machine shoots these fragments together at high speeds to build unique identifiers. It's the difference between typing a book on a typewriter using one finger versus using a printing press that stamps whole pages at once. They have already managed to encode all of Shakespeare's tragedies into DNA using this method. Once the DNA is written, you have a test tube full of trillions of microscopic strands. But how do you find the one file you need? You can't just press Ctrl F on a liquid. The solution is something called polymerase chain reaction, or PCR. When the file is saved, we attach a specific chemical tag, or address to the ends of the DNA strand. When you want to retrieve that file, you introduce a primer that matches that tag. The chemical reaction ignores the trillions of other files and starts copying only the file you asked for, amplifying it until there's enough of it to be read by the sequencer. It is a chemical search engine. This brings us to the red phase. Thanks to the Human Genome Project and the medical industry, reading DNA is actually quite cheap and fast. We have machines from companies like Illumina that use optics to take pictures of the DNA and handheld devices from Oxford Nanopore that pull the DNA through a tiny hole and measure the electrical current. In fact, new AI tools are accelerating this even further. Researchers recently released a tool called DNAformer, a transformer-based neural network that cleans up the noisy data from these sequencers, speeding up the reading process by over 3,000 times. So, if the technology works and the density is unmatched, why aren't we using it yet? The barrier is purely economic. Right now, the total cost of ownership for DNA storage is still too high compared to magnetic tape. For DNA to become a viable business, the cost of synthesis, the writing part, needs to drop by about 6 or 7 orders of magnitude. We need to get the cost down to around $100 per terabyte to make it competitive. There is also the issue of latency. You cannot run an operating system on DNA. You can't play a video game off it. Booting up a DNA drive involves chemical reactions that can take minutes or even hours. This means DNA won't replace your SSD or your RAM. Instead, it will create a new tier of storage at the very bottom of the pyramid. We call it cold storage, or deep archive. This is for the data that is too valuable to delete but rarely looked at. Legal records, scientific data sets, movie master files, museum archives. The roadmap for this is clearer than you might think. We are already seeing the formation of the DNA Data Storage Alliance, which includes heavy hitters like Microsoft, Western Digital, Twist Bioscience, and Illumina. They are working right now to standardize the industry, deciding what the physical cartridge should look like and how the files should be formatted so that a DNA drive written by one company can be read by another. By 2025 and 2026, we expect to see the boutique era. This is where high net worth clients in specific industries start using DNA for things like cryptocurrency keys, seed vault information, and national constitutions. By 2030, as the enzymatic synthesis technology matures, we will see the cold tier disruption. This is when data centers start replacing their acres of magnetic tape libraries with small, energy-efficient DNA kiosks. And by 2035, analysts are projecting this to be a $44 billion market. There are, of course, challenges to work out. There are biosecurity concerns. If we build machines that can print DNA at gigabit speeds, we need to make sure they can't be used to print pathogens or viruses. We need regulatory frameworks to ensure that data DNA is chemically distinct or cryptographically locked to prevent misuse. But the trajectory is clear. The era of silicon dominance is ending. We are moving from Silicon Valley to Carbon Valley. The future of data centers isn't a massive, humming warehouse consuming the power of a small city. It is a quiet room operating at room temperature with rows of small glass vials. Inside those vials will be the entire history of human culture, safe for thousands of years, written in the very language of life itself. It is a poetic irony. As we reach the absolute height of our technological advancement, generating more information than our machines can handle, we are turning back to the oldest, most sophisticated storage technology on Earth. Nature solved the data crisis 3 billion years ago. We are just finally learning how to read the manual, so the question is no longer if biology will merge with technology, but when. And when that day comes, would you trust your most precious memories to a synthetic strand of DNA? Or does the idea of living storage make you uncomfortable? I really want to hear your thoughts in the comments below. If you found this deep dive fascinating, please hit that like button and subscribe for more stories about the future of technology.